Okay, hello everyone. Today we're gonna be working on part 1 for project 4, and the first thing that you should do is really read the PDF very carefully to understand what you're modeling, and also because he gives you some important code considerations that you can literally just copy and paste into your system. So first, to understand a little better what we're gonna do is we're gonna be model walking. Walking can be modeled through two angles, and how these angles change. The first one is the theta angle, which is the angle that's formed between your hips and your first leg, and then phi, which is the angle between your two legs. And these are the two angles that we're going to be looking at. Now, for a model of walking, it has been shown that you can more or less model this behavior with this system of second order ordinary differential equations. And how we've learned to use ODE 45, we can really only model first order systems of ODEs. So in order to do that, we're going to transform this first and second equation into a system of 4 equations that are first dimensional ODEs. So in order to do that, we're going to introduce a new variable called y. Y is going to be a matrix in your Matlab, and the first column of that matrix is going to be your first independent variable in this system of equations, which is theta. Your second independent variable is going to be, you see it here, phi. The third independent variable is going to be the first derivative of theta, and then the second independent variable is the first derivative of phi, which makes a 4-column Y matrix. Now, if you remember from our previous projects, when you use an ODE 45, you can only have it depending on 2 variables, which is your time and then y, which is what ODE is finding at every time step, correct? Now, we have one extra variable here, which is gamma, which is what we're going to create a function called dy dt. Dy dt is going to depend on your time, your y, and your gamma. So the first thing that we need to do in order to create our Walker function is to define what y is. So just a little bit of code considerations on how I'm going to type things. I'm going to call theta capital T. I'm going to call phi capital P. And then now if we look at our equation 1, which is here, we know that the second derivative of theta is just equal to the sine of theta minus gamma, and the second derivative of phi is equal to this part of the equation here, which I have typed here. So it's the sine of the theta minus gamma minus the sine of phi times cosine of theta minus gamma plus the sine of phi of the first derivative of theta squared. So the first thing we need to do is to create that y matrix. However, it is your Matlab that creates y. So basically we're just going to be doing is assigning variables to each one of these columns. So the first thing we do is we can create theta, which I'm just going to call t. And I'm going to say that t is just equal to the first column of y. And then you can do the same thing for p. And then you can do the same thing for your third y. And again, your third y is the first derivative. So we are going to call this dt, which basically means the first derivative of theta. And then this is just going to be y3. And then you're going to do the same thing for dp dt. Okay, so now what that just did is it assigned each one of our columns of y are independent variables. Now what we're going to do is we're going to actually create the dy dt. So to create dy dt, we just look at y. So y is theta, phi, d theta, and d phi. So if we do dy dt, the first derivative of y1, so that is dy dt 1, that is going to be equal to the first derivative of theta. So it's going to be equal to dt dt, which is your same y3. Okay? Now, if we take the derivative of the second y, which is dy dt 2, we see that is the first derivative of phi. So you can go ahead and type that. which is the same as your y4. Then dy dt 3 is going to be, now we go to our y, dy dt is the second derivative of theta because y3 is the first derivative. So if we take the derivative again, we end up with the second derivative of theta. However, the second derivative of theta, we're not going to give it a name, we're going to tell it exactly what it is. So in this case, dy dt is equal to t double prime, which is equal to our sine t gamma. So we can go ahead and copy it. This is the first equation that is given in your PDF, which is your sine t of gamma. So I know this is a little confusing, but just write it down in paper. Know what y is, and then take the derivative of y, and then give those expressions. Now we can do the same thing with dy dt4. But now dy dt4 is going to be our second derivative of phi, because y4 is phi prime. So dy4 dt is phi double prime. So you can go ahead and type this equation here, which is the same equation as I have written here. And then that just created your y's, and then it creates your dy dt's. Something that you might want to do here is to create an empty vector of dy dt's. And this is because you're going to get a warning sign saying that you're basically creating a vector one at a time. It's better if you create an empty vector first and then start filling out each one of its components. So you can either do this by just telling Matlab to create a vector full of zeros. And we have 4 columns, so we're going to give it 4 columns here, or 4 vectors here. You can also do this by using the zeros command, which is basically dy dt is equal to zeros 1, 4, or 4, 1 to make it the same thing. You can use either of these 2 commands, and then you can go ahead and create your dy dt d3. I've seen a lot of mistakes when you type this second with your dy dt4, and it's because, so when you bring that to the other side, when you bring all of this to your other side to find the second derivative of phi, you put this in positive, but then you distribute the signs here wrong. So make sure that this first part is negative, because when we bring it to the other side it becomes negative, and then the second part here is positive. So in order to avoid confusions, what I did is I distributed myself that sign of phi. So I say, okay, phi double prime is equal to a positive sine t minus gamma, then negative sine phi cosine theta minus gamma, and then positive sine theta prime square. So that is just the most straightforward way to do it, to make sure that you don't have mistakes on your function. That's all you need to do for your dy dt Walker function. So now we go back up to our into our code itself, and then what they ask us to do in the PDF, if we go down here, is okay. So first write the function, which we already did, and then the second thing is to use ODE45 to compute t and y, knowing gamma, which is what he gives you here, and knowing also our initial conditions. So I'm sure you're all very good at creating ODE45's functions now. So again, we start with t comma y, and then we do ODE45. And then again, the first thing that we need is a function. However, our Walker function depends, as we see, on ty and gamma. And our function in an ODE45 can only depend on t and y. So what you can do is you can create a function called fun, or whatever you want it to be, and then make that depend only on t and y. So you can make an anonymous function, say t and y, and then go ahead and type your Walker function. Walker t comma y comma gamma. Now what this is going to do is it's basically making that Walker function that used to depend on these 3 things make only depend on t and y, because we already know what gamma is. Gamma is not a variable anymore, now it's a constant. You can also put Walker t comma y comma 0.011 if you want inside your ODE. This is just a more straightforward way to do it. Now we can write our function here called fun. The next thing you do is need is a t-span. So again, if we go to the project description, we see that he wants us to do from over a period of time from 0 to 5. So again, we just have to say 0 and 5. Then the next thing we need is our initial values, which is why not. We already have why not. He gave it to us. And then the next thing we do is we need is our options, which is what we used to call our OPT. Now, as you remember last time, OPT allowed us to make sure that our solutions were always positive. Now this time, what they ask you to do is to use error tolerance. So if we go to the PDF, it tells us in the project use ODE 45 with both relative and absolute error tolerance set as 10 to negative 12. In order to do that, what you need to do is just create an option. So basically what an option allows us to do is to tell ODE 45 our physical constraints or our mathematical constraints. In this case, we want our relative tolerance, which is same thing as saying our relative basically error, to be 10 times 10 to a negative 12. To do that, we're gonna do the same thing we did last time when we did the non-negative, where we're gonna create a variable called OPT, and then we're gonna use the function ODE set, which is what we used last time. We actually don't need this parentheses, which is that ODE set, and we're gonna tell it, okay, I want the relative tolerance, which is the first option that is going to show up here, and then what do we want it to be? So go to the reading and then figure out what the relative tolerance should be, which is written right here. So we give it the number, and this is just a placeholder. You write down the actual number. Then we want it tells you you want the relative and an absolute tolerance. So now we're going to do absolute tolerance, and then we're going to give it the number, whatever the number is for the absolute tolerance. And what this is going to do is just when Matlab is solving the ODE, it's going to take into account that you want the relative tolerance to be a certain number and that you want the absolute tolerance to be a different number. And when you add this OPT into your ODE 45 function, you're making sure that you're adding this constraint. So if you create an OPT variable, right, but you don't add it into your ODE 45, then you're not doing anything. So make sure it's right here. Now you've created a T and a Y matrix, and then you just have to plot it. So I've already showed you how to plot this. Remember that what you want to plot, if you go to your PDF, is you want to plot theta and you want to plot phi. Theta is your first column of y and phi is your second column of y. Remember that if we have a matrix called, for example, 0, 1, and 2, and then 3, 4, and 5. Sorry, I forgot the equal sign. Okay. So this is our matrix. If we want the first column, what we do is we say, okay, give me the first column of y. By doing that column, we basically generate all the rows, and by putting a y, we tell it only the first column. So this is exactly how you need to plot. So just use your plot, your normal plot, and then it's over time, and then tell it which column of y you want to plot. And this is what I meant to say t. Okay, so you say plot t, which is your x, and then y, then you can do the first column and then the second column the same way I showed you here with a. Now, say for example, I wanted columns 3 and 4. Then what I would do here, I just wanted one of the columns. If I wanted columns 3 and 4, what I can tell Matlab to do is okay, I want all of the rows, which is what you do when you say column, and then say, but now I want columns 2 and 3. And this is how you type it. So now you get 1, 4, and then 2, 5, which is 1, 4, and then 2, 5. So you can do the same notation for your plotting here. And then don't forget to add your X labels and your Y labels, and then that's it for part 1 of your project.